Hi guys, sorry I can't be there today, so I'm going to run through the study guide fairly quickly as your warm-up, and then I have a couple limiting reactant and excess reactant problems to work through. I'm going to work through this quickly so that we still have time for the test. So here we go. In balancing the first equation, I would see that there's 1 sodium on this side, 2 sodiums on this side, so my initial reaction would be to put a 2 out front here. Next I would look and see that I have 2 iodines now, but on this side I actually have 4 iodines. So rather than a 2, I'm actually going to need a 4 out front, so my iodines are balanced. But now in fixing that problem I've created another problem. 4 sodiums here, only 2 sodiums there, so I'll need a 2 out front of this sodium. That gives me 2 sulfates, which is nice because I have 2 sulfates here. 1 lead here, 1 lead here, 4 iodines, 4 iodines. So now it's balanced. 1 and 1. Next problem, looks like I'm going to need to do a 0.5 maneuver with my oxygens. I can tell that because of this hydrogen. So I'll start off. 2 carbons on this side, 1 carbon on this side. I need a 2 out front. 6 hydrogens on this side, 2 hydrogens on this side. I need a 3 out front. Now my oxygens. I have 2 times 2 oxygens for 4 oxygens here, and 3 times 1 oxygen for 3 oxygens here. So 4 oxygens plus 3 oxygens gives me 7 oxygens on this side. What number can I multiply 2 by to get 7? The answer is 3.5. And to finish it off, that would be a 1. But we cannot have 3.5 oxygen molecules. So to finish this problem off, we have to multiply the whole thing, all coefficients, by 2, and we end up with 6, 4, 7, 2. Final answer's there. Last problem. As I look through this problem, I see that I have 2 ammoniums there. Remember that you always get to balance polyatomic ions as a unit. So there's an ammonium there, there's an ammonium there. On this side I have 2 ammoniums, on this side I have 3 ammoniums. So what number will 2 and 3 both go into? The answer is 6. The way you make 2 6 is by multiplying by 3. The way you make 3 6 is by multiplying by 2. Now my ammoniums are balanced. Now on this side I have 3 sulfates, because remember SO4 is another polyatomic ion, so it gets balanced as a unit. 3 sulfates there, and fortunately 3 sulfates there. Now I have 2 irons here, only 1 iron there, so I put a 2 out front. That means that I have 2 phosphates. Remember that phosphate, also a polyatomic ion. And wouldn't you know it, 2 phosphates there. Chemical reaction looks balanced, 3, 2, 2, 1. Alright, now we need to convert 118 grams of iron to moles. When you're asked to convert to moles and not given moles of a new product, all you're doing is going to moles of iron. So this is a one-step dimensional analysis problem. 118 grams of iron. Only one way to get rid of grams of iron. It's with grams of iron. And then we can go to moles of iron. Whenever it's grams to moles, moles to grams, it's always 1 mole. And then the atomic mass of iron is, as I look at the periodic table, 55.8. I'm going to call it 56, because why not? When you do this, it's going to be 118 divided by 56. 56 times 2 is 112, so it's going to be about 1. I think we're going to call it 1.1 and call it a day. There should be another sig fig there, so we'll call it 1.10. If you actually calculated it out, your answer should be close to this, but I just had to do it really quickly, so that's what we've got. Moles of Fe. Final answer. Alright, so next we have problems 5 and 6. 5 looks like we're going from moles to, or rather from grams to moles. So I'll start off with my lonely number. Looks like it's going to be 52.6 grams of H2O. This looks like it's going to be a two-step dimensional analysis problem. I'll have grams of H2O on the bottom to cancel them out. I'll go to moles because that's how I convert between different substances. Always 1 mole. H2O weighs 18 because oxygen is 16 plus each hydrogen is 1, but I have 2 hydrogens. So 18 total. Now I'll need one more parenthetical statement. And if I want to get to moles of methane, I'll need to cancel my moles of H2O. So we've got moles of water on the bottom, moles of methane on top. Now, the way I get this is from my balanced chemical equation, so I need to balance my chemical equation. So when I look at this, I see that I have 1 carbon there, 1 carbon there, we're good. 4 hydrogens there, 2 hydrogens there, not so good. But if we put a 2 out front, that's balanced. And now I have 2 oxygens there, 2 oxygens there, so 4 total. The way I get 4 over here is by adding a 2 out front. So my coefficient should be 1, 2, 1, 2. Final answer. So now in front of methane, I have a 1. So in front of moles of methane, I put a 1. And in front of H2O, I have a 2. So in front of H2O, I put a 2. And then it's 52 divided by 18 divided by 2. 18 times 2 is 36. So 52 divided by 36 is going to be right around 1.5. I'm going to call it 1.5. You should do the actual calculation to see what it is. Again, my sig figs are incorrect, so I'm going to throw a 0 on there. This is probably not the correct answer, but it looks like it's pretty close. Moles of H2O. Final answer. Alright, last one is a grams to grams problem. We're going to have to do a couple grams to grams problems in our limiting reactant problem, which is below. So I'm going to skip this one. The gist of it is balancing the chemical equation. This one's a little tricky to balance, so I'm going to go ahead. We've got 1 silver here, 3 silvers there. So initially it looks like we're going to need 3 silvers. I have 3 tins here, only 1 tin here, so it looks like I'm going to need a 3 out front. I have 4 phosphates here, only 1 phosphate here, so I'm going to need a 4 out front to balance that, but that screws up my silvers. Now I have 4 times 3 silvers, which is 12, so this is no longer 3. I have to just change it to 12. 12 silvers, this should stay 1, so 12, 1, 4, 3 looks balanced to me. Then what you'll do is you'll go 217 grams of tin. I'm not going to fill in the numbers, I'm just going to fill in the units so that you can see. Only one way to cancel grams of tin. It's with grams of tin. And then I'm going to go to moles of tin. You get the numbers from the periodic table for grams. Always 1 mole when it's grams to moles. I am going to fill in the numbers. 119, it's 118.7. If you used 118.7, you'll get an even better answer than me. Cancel out moles of tin and go to moles of silver. Because it asks us specifically in this problem to go to grams of silver, I have to go to moles first. Looks like in front of silver I've got a 12. Remember that the balanced chemical equation is always used to find the mole to mole ratio. And then in front of tin I have a 3. Final step, because when it's grams to grams it's always 3 steps long. We'll have to cancel out moles of silver and go to grams of silver. Always 1 mole when it's grams to moles. Grams of silver on the periodic table looks like it's 107.8. I'm going to do 108. If you did 107.8, you'll get an even better answer than me. And then what you'll do is you'll take 217 times 12 times 108 divided by 119 divided by 3 divided by 1, and you'll get an answer. That answer will be in grams of silver. Alright, I'm not going to solve... I am. Never mind. I lied to you again. Alright, this problem says, in the reaction above, if you start with 640 grams of silver and 1,460 grams of tin 4 phosphate, remember I'm calling that tin 4 phosphate, not because there's 3 tins, but because the charge on that tin is 4. So tin 4 phosphate, what will your limiting reactant be? And so we're going to start with 640 grams of silver as a lonely number, and we're going to start with 1,460 grams of tin 4 phosphate. And remember, we get to pick which compound we convert to. Limiting reactant problems, there are always 2 sets of dimensional analysis, and you get to pick which units you go to. So let's take a look at that equation really quickly. So silver we're starting with, and tin 4 phosphate we're starting with. We can go to either silver phosphate or tin. I'm going to pick tin. Whichever one you picked, the limiting reactant won't change, your math will just change. So here we go. I have to get rid of grams of silver by using grams of silver. Then I can go to moles of silver. 1 mole for 108 grams. If you use 107.8, you're a better person than me. Then we'll go moles of silver on the bottom, moles of tin on top. From our balanced chemical equation, it looks like we have 12 moles of silver for every 3 moles of tin. So 12 moles of silver for every 3 moles of tin. One final step. We'll have moles of tin on the bottom, grams of tin on top. For every 1 mole, tin weighs 118 grams. 119 grams. You'll calculate an answer. On the bottom, you do the exact same thing. Tin 4 phosphate. So immediately we start off with a challenge of figuring out how the heck much tin 4 phosphate weighs. Well, tin weighs, we're going to call it 119 times 3 plus 4 phosphates, so 31 times 4, plus 16 oxygens. Oxygen weighs 16 times 16. So 119 times 3, if it was 120 it'd be 360, so it's 357, plus 31 times 4. If it was 30 times 4 it'd be 120, so it's 124, plus 16 times 16 is 256. I know that because computers used to only have that much storage. Okay, now when you add all those up you'll get a number and you'll put it here. Looks like it's going to be in the 700 range and change. 700 and right around 50. But math is hard, so that's what we're going to be okay with. To 1 mole of SN3PO44. Next step will be our mole-to-mole ratio. We'll have to get rid of moles of tin 4 phosphate and go to moles of just tin. And if we look back at our last equation, in front of tin 4 phosphate we have a 1. In front of tin we still have a 3. So a 3 and a 1. And this last step will be the exact same as the one above. 1 mole of tin for 119 grams of tin. You'll get an answer. Whichever is smaller, that means that either silver or tin 4 phosphate will be your limiting number, depending upon which one of these answers is smaller. There's one more video for you to watch. It's 2 more limiting reactant and excess reactant problems. So Mr. McKee, you could play those now. They should be on a tab right next to this one.